Today we are going to do the three last chapter. Last chapter being a really small project where we can basically blend everything we have seen so far. And today we are going to start with generics. And generics is something we have already talked about when we saw options and results, because those two are enums carrying generics. And so let's start. So we'll close that. Okay. Why generic exists? Generic exists because, as we saw, Rust, everything is done at compile time, and it's also strongly typed, and that's maybe where it's interesting. When it's strongly typed, it means that every time you need to define a new specific structure for carrying, for instance, a given type, you would have to create a new implementation of such a structure. So generics are just there to create some kind of templates around structures or enums, so that we say, okay, you can put whatever type inside this structure or this enum, and it's going to be resolved at compile time, and the compiler will just generate the appropriate structure for that specific type. So it's mainly there to avoid code duplication. And obviously, it guarantees a lot of the other aspects of the Rust language. So it's type safe, it's zero cost because everything is done at compile time. And it's also, yes, very flexible because you define the type and you define the struct or the enum once, and then you can use it at multiple places. So as we have seen, and as I said, we have already saw generics quickly when we saw the option, which is option and results, which are two enums carrying generic types. So let's start with generic that can be used not only in structures and enums, but only in functions. And first, we just illustrate like the redundancy of creating um, two functions actually doing the same thing, but on different types. So what it does, those two small functions, both are doing the same thing. They are getting the first item and the last item in a slice. So here it's a I32 slice, and here is a F64 slice. And okay, we can just run the test and see what happens. So here we should get 1 and 5, and there we should get 5 and 1. Okay, that's what we got. And can anyone tell me why do we return an option here? Subsidiary question, nothing to do with generics. Why do we return an option?
Because first and last are option.
Yes, of course. And yes, basically because how to say, if there is no item in the list, it means we might be, it's like interesting to return none in this case instead of something. So the exercise is what it's, let's implement a generic function that will be able to work with both the slices without having to create two separate functions. So Fn This is function definition, first and last. And here is the trick. It's like where it's the same thing when we define lifetimes. We have to put like angle brackets here. And we say we define a generic type. Most of the time in Rust, we use T. This is completely arbitrary. We could use Z. I don't know. We can put foo. It is like whatever we want. It's just that later we will have to use exactly the same when we use that type, for instance. So we just define the function prototype. So our function prototype is going to take what? Any idea?
List of T, slice of.
So it's going to take a slice of T. So how do I declare that? I declare like the slice, and instead of putting like the type I want, I just put T. Okay? It's pretty easy. And then what do I return?
An option of TT.
An option of tuple?
Tuple.
Like this?
Yeah.
Okay. Yeah, that's correct. So you see, it's not much complicated that just replacing our types by a generic type. And the generic type here is called T and could be called whatever we want. It's up to us to choose. And that's it. And the only thing you have to remember is that you always have to, when you define a function here, because why here we have to define this? This is maybe a specific case because this function is not associated to a structure where T is already defined. Here, T is not defined before, so we have to define it here in angle brackets. And not much complicated, that just calling the exact same stuff on the slice. And yeah, this should be called slice.
Can we create an enum of T and don't call it with the bracket at first and last?
Tell me, so an enum?
Yeah, but before the function definition.
Okay, so you would do what? An enum of what?
Of
How we call it?
T.
T?
Yeah.
Okay.
With E32 and F64.
I32 like this,
Yeah.
and F64 and F64, and do a slice of T like this, you mean? Do a slice of enum?
Yeah.
Yeah, this would be kind of possible to achieve the same goal. Instead, that every time you have to add a new type, you have to add it to UNum. So, I mean, it's not like super convenient. While here, it's super easy. It's just like the compiler that replaces T by whatever type you are, whatever slice you are providing. So it might be a complex structure, it might be anything. And you don't have to do anything manually. It's like the compiler does it for you. Of course, you could do something like this and create a slice of T, which would like kind of allow you to achieve the same stuff while
Because it can be more restrictive, like for people to, and for also for people who want to develop on the first and last function to know which real type they can use instead of generic T.
Yeah. But here, if you do that with Genum, what could be the trick is that in your slice, you might be able to have a blend of I32 and F64
Yeah.
inside your slice.
Yeah.
which is completely different from having a generic slice of one single type. You see the difference?
Okay, because with this slice, we can only put in it E32 or
Yes.
F64.
Yes,
We
yes, yes.
cannot,
No. Yeah, because it's again, Rust is compiled. So what you are trying to do is behavior that you find in Python, JavaScript, and so on, like languages which are interpreted and where you can basically put whatever object and blend objects into structures and slices. But here in Rust, you always need to know the type of the data you want to put in your data structure. It's not like, yeah, you put whatever you want. If you want to put like something which is whatever or almost whatever, because it's always like a limited number of possibilities, right? So you would have to create something like this. But yeah, we wouldn't call it like, we would call it, I don't know, any or whatever. Any num or number, for instance. And there you could actually make a blend of numbers, might be I32, F64, whatever. You could add others here and create it and use it in a slice. So yeah, generic, it's just something that, and let's keep Decennium and we will use it in the slice as well. So what is nice is now we can just use this function with F64. So
yeah, it's that way it's generic because we can use it with F64 slice and also
yeah,
E32.
yeah. This is the thing. And actually the compiler does it generates what it does under the hood is actually generating these two functions because it knows that I mean, not exactly those, but something very similar, which means generating one function for each type, but it's completely transparent to you. So let's do it like that. And you see like the compiler doesn't complain because I mean it understands that it's gonna work. And we can try again. We run the test and we should get exactly the same results. Okay. So this is one use of generics. And you see, we could even create like I don't know, let slice or num slice, num slice or numvac, yeah. Num slice would have been okay. Damn it. We could do a number. We have seen I32, 42, and number F64. I don't know. Like this, okay? So here I just define a slice out of the numbers enum that you mentioned. And we see that we can also do the print ln first and last. So on the number slice, so num slice, we have to derive a debug here, otherwise it's going to complain. First and last. and it's first and last of num slice. So you see like the power, let's say, of the thing is like just define one function, and you can even use it like with custom enums or custom structures. And okay, here we get like the first, which is some I32, and the last, which is a F64. So yes, that's about it. This is a function taking generics as parameter. So yes, generics are generated at compile time. So if we try to define a generic function that is not allowed, the code will just not compile. So let's try to do something. What is the issue? The issue here, so we try to define the largest for a generic type, a slice of generic type T, and return the larger. And inside this function, we try to do a comparison greater than, okay? But not all the types in Rust have like greater than. Like if you have a slice of string, if you have a slice of like a custom structure that you have defined, a slice of this enum, for instance, we don't know how to compare, how to say one is greater than the other, right? So basically, the compiler will just tell you binary operation cannot be applied to type T. And basically, it doesn't allow us to define it. So do I explain that after? Yeah. Basically, there is a workaround. The workaround is pretty simple. It's called trait bound, and that's what we are going to see in the trait chapter. And this would be basically to say, okay, I want to implement this function, but for any type T, also having like a partial OR that allows us to compare. Okay? This is like a trait. Maybe it's a bit advanced to understand this notation now. It's just like colon, and you define the traits that you want your type to implement so that this function can actually work. And yes, in this case, so that it can work, your type needs to implement partial OR. There are several traits like this that, yeah, you use a lot of times, but I think the compiler even hints you about it. If you remove it, it tells you consider restricting type parameter T with trait partial OR. So it's pretty obvious. And maybe it even proposes to do it for you. No, doesn't ask you. So yeah, there are two ways to annotate that, and one is to say like this, and tells you alias for these equality checks and comparison checks, sorry. And this would actually work. But of course, the type we have to provide in the slice needs to implement that trait. If, let's say, we are going to take again this number and we try to compute the largest with this enum. Oh, sorry, that's not what I wanted to do. Okay. We take again this enum. We take the definition of the slice, and now we try to compute the largest on that num slice. What does it tell me? Tells me can't compare generic in function number with blah blah. The trait partial ORD is not implemented for a number. That's what it says. And why that? It's because we just didn't implement it. Maybe we can derive it, but it might not be what we want. If we derive partial ORD, it's going to work after that. But this is an implementation that will compare one-to-one I32 with I32 and F64 with F64. So if you want like a custom implementation of partial ORD, even like being able to compare actually I32 and F64, you would have to implement this trait manually. Like saying, I don't know, one I32 might be it's possibly bigger than F64, right? So if you want to do like such a custom enum, I don't say it makes sense. I just say like this is one possibility that you want to do. So okay, we have just seen like the restrictions we might have when defining generics in functions, and that's going to be the same for structures and enums. Any question about this? Pardon?
Now the comparison works.
Now it works because we have derived a partial ORD for, we could actually remove partial EC. And one question actually we need partial EC because for the equality. For the equality, when you want to do like this, for instance. But there is going to complete there, no? Okay.
Maybe it's okay. I mean, you can partial.
Yeah.
I mean,
And question you might ask yourself is why is this called partial EC and partial ORD? It's because there are some types where you cannot have like equality on or ORD. One such type is F64 because they have specific values. They have infinite, plus infinite, minus infinite, and they have none, I think. So which is like a specific value too. I don't remember for what, on Rush. None value. It's basically yeah, a specific value from F64 type. Doesn't tell. Maybe we can educate ourselves and just know what is none. Basically, all those three specific values cannot be equal to anything. So that's why there are traits which are EC, ORD, and those which are partial EC and partial ORD. And EC, for instance, if we want to derive EC or ORD for this one, it will tell us that F64 cannot, because F64 has those three specific values and they cannot be considered as orderable or equal to something. Because how do you compare like plus infinite plus n plus infinite? I mean, you cannot. So Rust STD. I'm just like checking what is like the non-value for F64 so that you get like an ID. It's like this. So not a number. Doesn't define just a single non-value, plethora of bit patterns. Makes the difference. Okay.
doesn't say anything about the use case.
Yeah.
It would be interesting to see.
I don't know. Maybe if you try to divide by 0 or something like this, it gives you none. I don't know.
Yeah.
Okay, so just have to remember we have some specific value for x64 for f64, which cannot be ordered or compared because I mean they are just like yeah, impossible to compare value like infinite and none. So and this explains why we have like partial egg and partial odd traits. Tell me, Ruslan.
Yeah, maybe so I did what you did, but it still complains me the compiler, not compiler, but I think it's
Extension.
yeah, the Clipper, but yeah, I think Clipper complains with the bigger sign in the
This?
list. Yeah, exactly. This. Yeah.
What does it say?
Well, binary operator operation bigger, greater than, cannot be applied to type %t.
Because you put like this, you put that.
Yeah,
No?
it is in brackets. Oh. But no. Yeah, it was like this. Yeah. And now you changed it to.
I didn't change anything. I mean, it's you put like this, but because we define it for t and not for like reference of t, right?
It's the try to save on this.
Okay.
Yeah, it's just when you save this.
I forgot to say that. I forgot to move it.
So now let's see generics in structure. So it's very close to what we have seen with option and results instead of being enums. This is inside the structure. And we kind of adopt the same notation as we have seen before with the function. We put like struct name, and then we have to define the type, the generic type, inside angle brackets. And let's say a point. We have x of type t and y of type t. And as we have seen, the compiler will just generate two different structure for every use we make. So here, in this case, is going to be like an integer point with i32 as coordinates. And here will be a point with f64 as coordinate. This is the same idea as with the function is basically compiler generating code for you under the hood and understands it's actually two different types now. So let's uncomment this code and try to understand what's the issue. Anyone knows?
Visualize the 64 wanted to do the next step.
So the issue here, it's because we try to mix two types. So X being i32 and Y being a F64. And here we see that the structure we have defined as two times the same type, right? So it cannot like basically know which one is the correct one because we try to mix the types. So there are two ways to fix that. One way is just like to put like i32 everywhere. And the other way is actually to introduce not only one generic type, but two generic types. We could put T and U and say, okay, like this. Okay, and yeah.
I have an interesting thing that I tried. If you reverse U and T in the brackets.
Yeah, it doesn't change anything.
This one's changed. It says it's a F64 I32. That's I do it's confusing. Maybe it's just the same, but it's confusing because
If you do like this, U and T,
yeah, see the mix is changed the order. I don't think the result is different, but it's confusing because you can't
yeah.
understand that X is the F64 and Y is
Yeah, in theory, you put it like in order of use in
Yeah.
your structure.
It just this may be confusing, but it's the same result.
Yeah, because
in the type.
actually here it doesn't tell you. Yeah, it's not like necessarily in the order. It just gives you the generics in order of which, in order of appearance that you have put it here. So I mean, it's correct. I agree, it's confusing, but I mean, this is also confusing because this is confusing.
Yeah.
So usually you put it like in the good order so that when you see your type, you may have a better idea of the thing. So this is the second stuff. And look, here it doesn't complain because actually T and U can be the same type, I mean.
Can you force it to be different? Or you cannot?
Force it, what do you mean?
When you create a structure to make sure that U and T are not the same type.
To make sure they are not the same type? No, I don't think so, no.
Okay.
No, you cannot force it to be different. And that's actually what we see here in the next example, where we create even like a point on a, let's say, 3-dimension space with 3 generics. I mean, yeah, sky is the limit. I mean, you can put as many generics as you want. To be honest, in practice, I don't. You should not see like a structure with lots of generics, maybe 1, 2, 3 maximum. You see frequently, but more than this, it's very rare, I would say. So here we see that we can even like define a structure with Z as being like an option. There is no issue with that because it's like a type. So we can replace, I mean, it can be used as a Z type, let's say, this option U size. We could even put a string, I don't know. We could put like, even a static string would work. So, okay, you can basically put whatever you want. So, how do we actually implement a function for a structure or enums with generic types? So the way is this notation, and what it means is implement method for points for any type T. That's what it what it's actually saying. And here you have to use that like kind of generic type declaration, and there you say for point taking this generic type definition. Okay. And yeah, what you can read is like, yeah, no matter what type T is, here are the methods that all points of T should have. So here it's a method which is actually swapping the two values, so X and Y. And here, this is a method from the standard library that allows you to swap two values efficiently. So that's why I'm using it.
Can you also swap values on the stack this way?
Pardon?
Can you swap values in the stack this way as well?
This will be on the stack.
Okay.
This structure should be on the stack because I mean, not this one because this is generic, but this one with I32 should be on the stack because the two values composing the structure is on the stack. The size of the structure is known, so it can live on the stack.
But if you had one of the next most points, and then you had one value on the stack and one.
If I would like put maybe another type here and a string, maybe it would be on the stack too, but string is a bit weird type. It's actually what they call a smart pointer. So, I mean, the pointer would probably be on the stack with the structure, but like the slice of the characters would be in memory. A smart pointer is basically a small portion of data we know the size of, which is like the pointer to the data, the size of the data, and I think that's all. And then it goes to somewhere in memory.
So in the end, no matter what type you use, the pointer is going to be on the stack anyway, and you can swap them.
Yes, I don't know whether that would work. I mean, if there the swapping works because we have two times the same type, but if we have different kinds, I don't know.
The example that we had before with the UNT, that would be.
UNT wouldn't work because I mean here the swap method, what prototype does it take? Look, it's type T.
Okay.
For the two values you want to swap, it must have the same type. Otherwise, it's not going to work. If you try to swap like a I32 with a F64, you can end up like with a huge mess.
Yeah.
And yes, you will again. This is like a Rust a philosophy of not like messing up with a lot of end up in really weird situation. So this method, yeah, just makes you swap two values of the same type.
Yeah, in Tableau, it's really.
So let's see now. Oh, what is the rest? Okay. And here we actually see that we can swap strings too. So it works because they both have the same type. And so let's see with integers. So
quick question regarding like the string stuff, because like in that case, I'm like, okay, I have like a set of types that would make sense to swap, but I don't want to have strings in that structure. Like, would there be a way to like do something about that? Like to be like, yeah, I just want like numbers, basically. I don't want any strings in my point.
Yes, you could enforce that. Yet, what would be basically what are you afraid of?
I'm afraid of like basically I want like numbers in my point, and I don't
Yeah.
want to have to deal with the case that someone put a string in it. Like basically, as it's hard typed, I want to just avoid. I don't want to have to care about this strings issue
So
in
my
my
next
structure.
question is how do you want people to put something you didn't expect it on your structure?
Say it comes from like the user input. I mean the easier like user input. Like
So
just
this is not possible because it means, I mean, everything is compiled in Rust. So it means
yes.
that if you want to handle user input, it would mean you would have to create such a specific structure holding the data
Mhm.
you want. And I mean, the compiler cannot like magically
Right.
put data you didn't plan into your structure. The structure needs to be defined at some point, and here
Mhm.
it's like it's defined here because we use
Yeah.
strings.
Mhm.
But I mean, like I cannot like magically create a point from user input that is different from the structure I actually define. This is not possible. So the only use case where I would see having like a strong, restricting on the type of the structure would be if you expose the structure to someone else in, I don't know, an API, a package, or whatever. You don't want like your structure holding specific type of data. This is the only use case where I see it would.
I want to do the sum, for example. Like I want to have to the sum of both values.
Yes.
So yeah, like basically like somewhere like I expose it and then at some point I do the sum. So I can't have strings in it.
Yeah. Yes, that's true. So you can actually do the same stuff. Maybe we can do it. So you would have like fn sum, right?
Yeah.
That's what you mean.
Yep.
It doesn't need to be mutable, right? So the sum will be of type T. Huh? So it's like self.x plus self.y. Okay?
Yeah.
Error. Why do we get an error? We get an error because it doesn't know how to sum x and y, right? Exactly the same point as we have seen above. It means for many types, you cannot sum the values as the strings and so on.
Yeah.
So you would have to introduce what we saw earlier, which is trade bound too. So you can either restrict it, I think, on the implementation block. You can say there T add. This is one thing. Okay, I need to import the trait. Why does it complain? Mismatch type. Expected this type parameter. What's the point? Type parameter T.
It's about the return type, no?
Let me see. What's the issue? Okay. Because T as okay, maybe this is not the way to do. Maybe the way to do is to put it here. No. Cannot add T to T. No implementation for T to T. Okay, because I have to put it here and here. Then no, it doesn't change anything. Then I have like a weird stuff. I don't know how to solve. Okay, I have to put a note add. Yes, I have to do that probably. No? Yes, okay. So here now it's complaining. This is correct. But the stuff it's complaining because again, it doesn't know whether that value is like living on the stack or on the heap because it might be one or the other. So we also have to restrict the fact that T must be a copy, so it lives on the stack and there it works. So yes, this you have to see it. Again, this is like complicated. I mean, this is something we we haven't seen yet. These leverage the trait implementation of the add function. And this is like a way to say that when we add, the output is going to be T, and that's what it was complaining about.
Right.
And the type T must also implement copy. And there, for instance, it's not going to work with strings, you see?
Mm-hmm.
It's
Yeah.
not going to work with strings because I mean strings is not implementing those. But what could have been done is that moving this even further up, you can restrict it directly in the structure definition and not on the implementation block. Actually, you have to do it on the two places. So that it's okay. And there, even the point will tell me, okay, cannot add string to strings because it doesn't implement the add trait. Because yeah, it's very flexible what you can do with generics, and this is called trait bound. The fact
Mhm.
that you are restricting the implementation your generic must have, this is called trait bound. So this is like very flexible what you can do with the trait bounds. You can put it either in the structure, you can put it in the implementation, you can put it in the function. So yes, and the error that you would get will be different.
Mhm.
Yeah, in function of the places where you have put your bound.
Mm.
But this would be like the way you would do to restrict the use of your point and not
Okay.
to hold strings. But anyway, let's keep things simple. Okay, you do
Yeah,
that.
no.
You do that and that. Yes, but now you wouldn't be able to sum the coordinates. Okay, so yeah, if you actually always want to sum, you have to put some trait bounds, otherwise you won't be able to sum the values. And there, yes, this would be the simpler implementation. And at the moment of your using your point with strings, it would tell you, okay, I cannot do it because it doesn't, it tells you, sorry, trait bound, like string slice, std ops add was not satisfied, so it cannot generate this implementation block for this structure. Okay, is that clear?
Yep, all good.
It's a bit complex, I think, right now to understand all of this because it blends both the generic aspect and the traits aspects.
Mhm.
But to be honest, once you used it like a bit, you get very used to that notation, and it becomes more obvious.
Yeah. No, I mean, I'm asking because like the kind of stuff that I've tried sometimes to do in Python with like the typing hints and so on.
Yeah,
It makes sense to be able to say, okay, no, like when you use that method, it can't be that kind of type, or when it's that kind of type, I need to do that kind of other, like just yeah, I need to like implement different stuff. So having a way to do that in Rust makes sense. I was just curious how to do it. So all good.
yeah. But just remember that okay, your structure when you define it, it's like, I mean, it's hard coded, so the type cannot change like that function of the user input, which
Yeah.
was, I mean, your original remark. This
Yeah,
is
yeah,
absolutely impossible in Rust. So
yeah.
don't be afraid of like misuse of this kind.
Yeah, but I mean, having the sum,
Tizio?
like having a method that expects to have like a sum is also like makes sense. So like having a way to just have something generic, but also generic without something is
Yeah.
makes sense.
Because this, for instance, would work for any type that implements the add method.
Yeah.
So we could now create a point of whatever integer or float. It's going to work exactly the same way, but wouldn't work for strings as we would see here because they don't implement it.
Yeah.
So yes, this is the power of generics combined with trade bounds.
Yeah.
My question was about can you implement functions for specific types? But I think this is kind of the
Yes, I think that's what we are going to see just after. We are going to see that in the next exercise. But yes, you can implement definitely just functions for some generics.
that might resolve the problem.
Let me see. Okay, no, maybe this is in the trait. No, this is there, for instance. And yes, we might be able to do what you wanted. So generic structure number 3, we take the exact same structure point, and here we generate a concat method which applies only and only for types being static strings. So instead of putting a generic type here, you see that we actually put a type directly. And you can, in this way, generate some functions only for that specific type. So that specific type would be string.
In generic solution, would you be able to overload the add trait, create your own that also?
You mean you wouldn't need to be able to create the add for strings, for
Yeah,
instance?
because in this case, I would have to create the add for strings for every implementation or for every structure that ever I wanted to have the add. But if I have a bunch of different structures and I want
You mean there?
No, where you where you define add, where you import add.
Yes.
Could you import? Could you overload that implementation of add with a different version where you define?
So you can this we are going to see it in the traits, but the traits implementation this is not called overloading because you cannot overload the method of a type which is not in your package. So I mean, there are two conditions to be able to implement a method. Either you have your trait in your package, so and you could implement the trait for even the types from the standard library because it doesn't come into conflict because the trait doesn't exist. And the other possibility is to have actually the structure or the enum inside your package. And there is absolutely no way you can implement add for strings. You could create your own add strings trait and implement it for strings, but you cannot like redefine the add methods on the strings from the standard library because it would create like a huge mess in libraries and in stuff like that, like people not knowing how add works with your implementation of your types or stuff like that. So there is no way you can re-implement traits, override traits for standard types.
Even if it's not because you have to import specifically the trait for add, it's not there by default. You have to add it.
Yes, I had to add it. Yes.
So if I added an add named trait with a different package path.
Yes, you could do that, but it wouldn't work with the plus, for instance. You would have to.
It would have to account for those cases too.
Yeah.
Yeah. But if you take the original implementation and add one more branch for strings, then you could overload.
Or what you could do is like you do a wrapper struct or a wrapper enum, and you say I don't know a struct my string, which is wrapping a string, and you would implement add for my string, you would do that. Then you implement the stuff, and what you would eventually do as well is to provide like a imp from string for my string. So it's how to convert and map one string to a my string. And this way you would be able to overload, I mean, kind of overload pretty quickly the add function because it would like do the conversion and all the stuff for you. So this would be very easy to do. It would be self value. So this is straightforward. And this we are going to see it because there we implement a trait. That's what we are going to see in the trait chapter. But when you define the from trait, it automatically also generate the other way around, which is the way to convert map my string into string. So it would like create the two implementations with only these 5 lines. So that's how you could somehow overload stuff without breaking all the existing stuff.
Another thing, maybe, can you implement the same function and the same name for this different type? Like you implement the add function, but if it's an int, you really add them. If it's a string, you concat them, but this is the same name for the function.
Yes, I think this is possible. Let's try to do it. We can do it now. Add. Okay. I think it's gonna work. Maybe we can reuse just this implementation trait so that we can actually because yes, the power of this trait bounds, what it is actually, it's so that I don't have to generate the imp block for every single type. I could do like imp, I mean 4.i32, 4.i64, 4.f64, blah blah blah. But here I just do it once, and that's good. But usually, yes, what? Ah, no, it complains.
Yeah,
Interesting.
the same name.
But why? Duplicate definition. Okay, interesting. No, so this is not possible. Yes, this is not possible, and it makes sense. It actually makes sense. Why? It's because here in your trait bound, you might have something that is which conflicts with this one. You see? There it's not the case, but you might be. There is no way to tell the compiler that there is no overlap between this and this. This is not possible. But he thinks that an overlap is possible, and so you cannot like define twice the same function name. Is that clear?
Yeah. Like, for example, if you force it to be an i32, maybe it will work.
No.
So one for the principal and one for the second.
So option crates may add a new imp. The definition. Yeah, this is weird. I just want to see something. Yeah, okay, this works. I will just try something. Self.x plus self.y. Huh. Okay, we'll just try to rename it. Okay, so I think the issue comes from the fact that it tells me that it's not, it's how I understand it, that this is possible that in the future the static strings actually gets add method, so it implements the add trait. So it cannot like duplicate this function. So that's how I understand the thing.
Yes.
So maybe let's try to do something. What could I do? Taking a type that I cannot add. Yeah, like a point. If I put like, no, this is not possible. Let's take the number enum that we have defined above. Maybe it's just because we have actually used the static string. Okay. After I tried that, we move to the next exercise. So it needs to implement add, right? And here I put number. Okay, so add is not is gonna be there derived. Okay.
Just a print.
Let's do something. No, I have to return something
Yeah.
because it's going to complain. There you can leverage. No, there is no quick fix. Yeah, no, it doesn't work. Okay. Let's do something simpler, which is not adding anything at all, right?
Yeah, just for that.
Just to see if it works. Why? Expected enum. Okay, okay. What? Ah, yeah, okay. I understand. Yeah. Okay, so it actually works to redefine it because it seems like the add is reserved for the string, which somewhere probably reserved in the standard library, and we cannot redefine it here. So
You can kind of overload the name of the.
so you can have the same method name for different implementation, let's say. That's what we just did. We did the edit for this this trade bound, and we did it like for the specific number. We might have an issue, look, if again we are going a bit far. if I implement add for a number, it's going to tell me that there is a conflicting implementation, I think. Okay. No? Why it doesn't tell me? This is strange. Why do I have this? Okay, this we don't care. Okay. This is strange. I would expect that it conflicts because this is applied here. Yes, because it doesn't implement copy. Because see, in the trade bound, I wanted add plus copy. So it doesn't try to generate this block because it doesn't implement copy. So let's try to, if I implement copy now, it's gonna conflict for sure. Because there we define twice the same method. It would try to generate it once for this and one there because number now satisfies this trade bound, which is it implements add, returning its own type as an output, but also it satisfies like the copy trait. So the compiler tried to generate this method once and twice for the same type, and it's not happy about it. But the good thing is that it tells you duplicate definition with name added. Okay, but to be honest, there we kind of went a bit far with this because we mix both traits that we haven't seen and generics. I wanted originally to keep that simple. And now this is a more practical example of a generic. This is an implementation of a FIFO data structure, a very simple one. So we define the structure as with the name FIFO member, which is element in the queue being in a vector. Why a vector? Because we can grow it and shrink it, function of the number of data which are inside. If we would have used an array, we would be limited to a number of items. And okay, we implement some function for that structure. So we create a new one. This is the constructor. We have some stuff to put items in the queue and a function to pop items from the queue. And here it's an example of a FIFO using strings. So we put first hello and we finally put world. So first in, first out. The first in was hello. So the first we should pop should be hello, and the second we pop should be world. So let's see if it works. Okay. And nothing actually crazy compared to what we have seen so far. So now we can just make any use of FIFO that we want. We can put any type, and this will be compiled will be generated by the compiler. So if we, for the moment, it tells me like unknown because we didn't put any type on it. And and you see it generates the FIFO F64. And this is like super convenient because we define like the structure once and we can reuse it multiple times with different types. And yeah, this is a super powerful features for compiled languages because if you think about C and Golang in the early Golang versions, they were not supporting generics. And for instance, if you want to define a FIFO, you would have to define a new FIFO for every type that you want to use inside a FIFO. And I can tell you that it's very, very boring to do because you have to re-implement every time the same method, every time the same stuff. It's just like copy pasting, but with different types. And basically, this is how you can see the generic. It just does all this crap for you. So just create a generic and let's say a template for your types, your structure, and then it gets applied at compile time. Very convenient. So we don't treat enums here because it's exactly the same stuff as structure, as enum being like super close to structure. You use it exactly the same way. I mean, it's not more complex than structures. So is that clear for you, the generics? Just there to help you and make your life better when you program. So next and last chapter, it's going to be trait. So let's start it now, and I guess we will do the break in the middle because otherwise we would break too early. So what a trait is in Rust, it's actually a way to define a shared behavior. So you have to think about it like a contract that says like any type that implements this trait must provide these methods. And your question is where we can actually use trait. So as we said, is to have like shared behavior between objects. But also I would go further is like exposing shared behavior to the outside because you could have like some sort of shared behaviors with enums as we have seen, like doing like an enums with different variants of all the thing we actually want. But traits go further because you can actually export those traits in your library. And so other people using your code can implement the method you are defining in your own traits. So it can also be used as code reuse because there are some you can provide also default implementation for traits, which is very powerful. We are going to see that. And you can achieve some polymorphism because different types can actually behave the same way. So you can see it more or less like interfaces that you have in OOP. What is very powerful is that you can define default methods, default implementation for methods. This is something we have already touched a bit, but you can use to restrict your generic usage when you are using generics. And yes, you can actually overload some operators for your type, for instance. So you could define like the plus for whatever type you are crafting. These are common traits that we have already seen along this training. So the debug trait, which allows us to print the debug version of a structure. The display trait that allows us to use the string formatting. The partial EC that we have already seen as well, which allows you to do equality comparison between types, and the from and into traits that we have already seen quickly that allows conversions between types. There are like a lot of other traits, but those are maybe the ones we are seeing the more. So this is the first thing to see is how do we define a trait. So we use the trait keyword, then the trait name. Here it's like greet. And we define like the methods, prototypes of the traits we want our, let's say, implementers to satisfy. So here the prototype of the function will be, we want greet taking the self, the structure or the enum itself, self keyword, and returning a string. So we could define a structure which is human. We implement the trait. The way we implement the trait, we have already seen that a bit too. You used imp keyword, then you use the trait name. So implement the trait greet for structure human. I think it's pretty straightforward, the notation, the syntax. And then it's even nice because if you look at Rust Analyzer, because you always end up like this, tells you not all traits, and you just start by F and propose you to implement the traits and creates you like the skeleton, and then you can just like copy paste and that's it. So implementing traits is pretty easy to do. So I define another structure, cat. I implement the greet trait for a cat with the greet function. And okay, it returns Mio, right? Interesting thing about traits is now we haven't brought like and we haven't touched like the visibility of traits, structs, and so on, because I mean I don't consider it's like something very specific to Rust, so I wanted to let you discover this. But in theory, when we define function, we have to put like the visibility in front of the function. Like here, if you, in previous function, let's say here, if you want a function to be publicly available for your structure, you put pub, okay? But for traits, what is different is that the visibility cannot be modified, and it's actually, it inherit from the visibility of the trait. So if your trait is public, I mean, people will have to implement this method, so the method will be public too. You cannot change the visibility of a method of a trait, which is, I mean, you cannot make a different visibility for the method than for the trait. Just something to know. That's not very important, but something to remember. And so here, just run, and we have created a human variable. Human says, hi, and Cat says meal. I mean, that's the expected output. Let's see. Okay, so we have a shared behavior between our two structures, our human structure and cat structure. Both implement the same functionality. Important aspect about trait definition is that you can actually provide default implementation for traits. So it allows you basically to give a standard implementation that works in many cases. And it can provide you some kind of overloading, some functionality in case of need. So it's called like an opt-out behavior. If you are not satisfied with the default implementation, just implement your own. And it can keep the trait definition very simple. And this is the single source of common logic. This is very nice. I will show you something just after this example. And look here, we redefine the trait greet always with the same greet function. And we provide a default implementation for another method, which is called print greeting, which is actually just println the self.greet method. So here we can call the method because it knows it exists because we defined it in the trait. If I try to use, I don't know, ABC, of course it's going to complain. It will tell me like, okay, I don't know ABC. I mean, what is this method? So here it works only because self.greet is already defined in the trait. And so here, as you have seen, as you see, I define the same greet function as we did above, and I call print greeting instead of doing the println myself. And we should get hi and meal. So this might look a bit dumb. You might wonder why is it useful. I will show you something in the standard library, which is like the read trait, which is something you want to implement for any IO structure. The only required method is read that takes itself as a first argument and a buffer and a result as an output. And all the rest are derived method from the read, right? So when you implement read, you get all these methods for free. And this is where it becomes like very interesting to have like a default implementation for traits. It's because you can directly offer to people implementing only one or two small function a number of other functions that might help them a lot with dealing with their structure, let's say. So yes, you have this for read, you have this for write, I think. The write trait is the same. You just implement write and flush for your anything you want to implement write for, and it provides you all these default implementations. And that's exactly what we did here. This is the only required trait. And after that, it generates this automatically. And we could, if we're not happy with the print greetings, we can change it. right? And we are not obliged to change it for all the types. Look, here I just changed it for human. I didn't change it for cat. So now when I print greeting for human, I am expecting to have custom greeting for human and saying hi. So it allows you to do very flexible things.
And quick thing from from the trait itself, is it possible to find like the name of the structure? So my point would be like to find in like in the print greeting to have structure name says greet. Like the same way I would do like self underscore name. Like is there like any like default like to find the name of the structure from the trait itself?
I will tell you something that I told Andras, but no one else knows. There is no introspection in Rust. It doesn't exist. There might be some macros or stuff like that that might gives you the structure name. I don't know if there is one. Probably. But anything relating to introspection that you would solve with introspection in other languages, you would have to solve them with macros in Rust and proc macros. So, I mean, is inspecting the codes that you are generating. You are you
compiling,
want to generate, to compile.
Yeah.
So yes, this might be how I would do it. I don't know if there is some macros to get the structure name. Probably it exists. But yeah, don't worry. There are ways to solve this kind of issues. But to be honest, this is something you want to use in this example, but in practice you don't use it a lot.
Yeah. I mean, I could see it for like debugging, like just have like a lot of like different structure how to figure out like where in my have a really complex how to figure out like where it's problematic, like just having mostly for like debugging purposes, I would say. But yeah.
Yeah. What you could do simply is like I don't know if there is you could always what would I do maybe let's see something first. This is something I've never done, so I don't know if it exists. Yeah, okay, it proposes you to use a macro in German. Thank you, Google. Yeah, probably there is some. It doesn't seem there is something standard to do it. But anyway, what you can always do, I don't know, is like instead of returning this, you would say format. Either you could use a self as a stuff and says hi. If that's okay, it's not happy because self doesn't implement debug. But yeah, to be honest, this is not the kind of things you are. This is probably something you think you might need coming from other languages, but I tell you this, you don't need this. Or this is something you will very rarely use, like the name of the structure or whatever, I almost never use this kind of stuff.
I mean, if you rely a lot on generics, you probably want to.
If
you rely a lot on generics,
Yeah.
you probably want to have
this,
for introspection at least.
but what would be the use case? Give me one concrete use case of this.
Because indeed, if it's functions, you would define them per type, so you don't care.
If anyone has like a concrete use case of having like the struct name inside a string, I take it.
You can always solve it with a function trait.
What is like a log message?
Yeah,
Yeah,
generally
it's
it would be log like
message.
my use case would be like a log message. Like just I have a code running for a long time on something somewhere goes sideways. When something bad happened, I want a log message to know what caused it. Like something that
And
is
how
like
is it better? How is it better to have the struct name rather than like a line
I know, I
and the
mean, like
file where
what you
it?
did, what you'd be I mean, I don't. I mean, I don't know. I have cases in Python when I have like I had like somewhere on when something goes sideways, I have a log message telling me where it came from. But like the format, like what you just did here is probably solving my problem. Like if you just like using like self like that would probably just do it.
Because what you
Yeah.
would do in a log message, at least what I would do in log message, debug log message, is putting where it's happening, like in my file, like the file name and the line number. So I mean,
That's actually trickier
Yeah.
if you're debugging the code
It's
based on the version that.
yeah, but this is like up to you to do proper version tagging. And if you in Rust, I mean, this is super easy to include like the commit tag name or whatever in the version, and you say, okay, give me your version number. You go back in the commit. Okay, this might be a bit complex, but yeah.
Yeah, I mean, that's probably I can probably live with what, that kind of stuff. It was just like curiosity if there's like anywhere. So there is no introspection, which is like a good information.
Yeah,
Yeah,
there is absolutely no introspection, and basically the way you do introspection is with
yeah, macros.
procedural macros.
Yeah,
The one where that we use like this. This does some kind of information introspection.
yeah.
But again,
That
this
would do
is
that.
like everything resolved at compile time. So introspection is something highly dynamic. This is something you do only at runtime. And this can cause like lots of issues too. And this is like just not possible and not in the Rust philosophy to do like this. If you want to do all solve any introspection issues, you have to use procedural macros. But yeah, that's kind of another topic, and you need to understand already a lot before doing proc macros. It's like higher level of complexity, I would say, because you actually get access to the parsed Rust code and you modify it actually, and you
Right.
generate new code based on what you have parsed.
But you could also solve it by having a trait that requires you to have a get type or whatever function.
Yes, you
And
could
then
do
based on
that.
that,
Yeah, you could do that if you just want to have like if you just want to have this for custom functions, there are ways to do it. I don't know. You can develop a procedural macro. You can create a macro. You can define your structures inside macros, which I don't recommend, but there are plenty of ways to do that. Yes, and having a trait just returning like a struct name, this is something you can do. But to be honest, this is not something I've been using so far. And maybe that's the good moment to mention it. At some point, you will realize that there are just some stuff that are not applicable between what you know and what you want to do in Rust. So you might just try to imagine things differently, and it's source of headaches in the beginning, but in the end, when you get used to it, and it becomes normal. It's just because Rust is like completely different from other languages that you would have to do this brain gym, I would say. But once you did it like several times, it just super easy. But yeah, don't get frustrated if you get blocked and you try to do something that you were able to do in a language you know. Maybe just try to see things differently, and yeah, maybe you can just reach me and I will tell you, okay, do like that or whatever, and it's gonna be simpler to do it like that in Rust. You just need to put your brain in Rust mode. So okay, let's explore the trade bounds with something we use with generics. So we have already seen it. It's to restrict the use of generic to some types implementing the traits, for instance. So it allows you to do some sort of polymorphism, so treating different types uniformly based on their shared behavior. So uncomment below code, let's understand what it's doing. Oh, it's not compiling. Damn it. Why is it not compiling? Any idea?
We only defined it for 2 types, and we might have a different struct that we try to greet on because it's a generic.
Yeah. So T, as we saw, is generic. So this instance of T is a generic type here. And here what we we create the function greet for any type T. But not all the type T have greet function, right? So in order to be able to use the greet method, we have to say, okay, this method works only for the types that implement the trait greet. And that's what we have seen in the previous exercises, and that's what we are going to do here to put like what we call, this is called trait bounds. So you actually put bounds to your trait so that it's restricting the function only to the types implementing those traits. And this trait is greet. And magic, it works. And we can call greet. Oh, sorry, greet for human. This works because human is like a unit struct, right? You might have the feeling it's a weird notation, but it's just because it expects like no parameter, no member. It works. It says hi. Okay. Is that clear for the trait bounds? We have already seen like much more complex trade bounds in the previous exercise than this one. So I think if you didn't block for in the previous exercise, this should be fine.
Just a quick one. If you wanted to have multiple conditions, you would just comma and add the other traits, right?
There?
Yeah.
You add plus.
A plus, okay.
Plus partial egg, plus
Right.
blah blah. Yeah, good question. There are several ways to mention trade bounds. There is this syntax, okay? Or you can put a where clause. This is called a where clause at the end. Oh, what the hell? T implements grid. This is another notation that you might see, another syntax. This way you don't get like super long function prototype with plus 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 plus. If you have like a long list of traits you need to implement, a huge trait bounds, just put it like this. And especially if you have several traits, like I don't know, UV, blah blah blah. You put them like and you can put this is the notation, basically the syntax. I'm just using it so that it doesn't complain. And you can add plus there or plus there, like I don't know, toString. And it's not mandatory that both the generics implement the same types, right? There is something, this where clause, you can use it everywhere. I mean, you can use it also in the function definition, in the structure definition. Basically, every trait bound you put there under the angle brackets, you can put them in a where clause at the end. For instance, if I want to define a structure, I will just put it, sorry, I correct that so that it's clear. So you want to create a structure. Taking a generic, right? You want to restrict this structure for something that implements grid. So you can either do it like this, as we saw, or you can do it with the where clause, exactly the same.
A dumb question, can you mix and match the two notations?
Good question. Let's try. I don't see why we wouldn't be able to do it.
And if you can what happens if you define T, for example, in both?
If I define T, what?
If you define the
there and there
for T in both, yes. So if you set Greek,
this is okay. I think if you define it twice, it's going to complain.
Okay, so there is no precedence which one it will take.
No, it even doesn't complain.
It's different. Like,
Yeah.
for example, the one T is a partial egg and the other T is grid.
Is it add them or does it?
But this is the same actually.
Yeah.
Okay, this is not like two different T. This is the same. You just say T needs to have grid. So if I put like a partial egg there, it's gonna work.
Yeah, it's gonna add the two.
Yeah.
Okay. Yeah. Yes.
It's gonna work. It's just like
Why would it?
In theory, either you see this notation or you see this syntax or this. You never see like a mix of the both. It's yeah. You will see like Rust developer most of the time are very picky. So this is like the kind of thing that you would never see in any code.
Like for example, what I can imagine is like there is some traits like that are important and specific that can be put in the first line of the function, and some other traits then can be on the where yeah, like the non-usual things can put on the specific things on the
yeah. Anyway,
maybe or I don't know.
yeah. I mean, I don't see why you would like to do that, but I mean, this is very clear as well, huh?
Yeah.
To be honest, usually you use this notation, this syntax when you have maybe one or two traits to implement. When it becomes more complex, you have like to chain a lot of traits or complex trait bounds. You put it in a where so that it's clearly separated. Yeah, it's just two syntax to do the same thing. And it's the same for enums, it works exactly the same. Either you put it under the angle brackets or in a what it's called a where clause. What remains? Okay, as you want, either we finish this and we maybe we have like for 15 minutes and we start back at 1 so that we keep our 45-minute breaks, or we finish after lunch as you want. You want to finish this and we do the project after lunch? Yeah. So let's investigate a bit more what the derive procedural macro is doing. So it automatically implements command traits for your types. So instead of writing the manual implementation of the traits, you can derive and trait name. This is what we have been doing for debug a lot and for other traits. For default as well, we have seen, and PortSelect and clone. So this is something you put above your struct or your enum. And what it does basically it just tells Rust generate the code needed to make this type debug clone or PortSelect. It's so that it saves you from writing boilerplate code because most of the time would be like basically the same stuff you want to do for all your types. Because what it does when it does derive, it derives every member, for instance, of a structure. It uses basically here it's format method, and it's gonna call the format method for every single member of the structure, and that's the same for enum. And if one of the member is lacking the debug implementation, it's going to complain because it doesn't know what to do with it, right? So yes, it only works for traits that can be automatically implemented. One important thing to remember, this is the same name as a trait, okay? But this is a procedural macro. So this is not because the trait exists that the procedural macro exists. The procedural macro, it's something that you need to write. the debug, PowerShell, and so on, these are stuff which are implemented in the Rust standard library. If now you want to implement, you want to derive your own traits you have created, you would have to write the procedural macro to derive this trait. This is not something which is automatic. Yes, so that's clear. You derive debug for person, and then you are able to call to use the debug version of the person. That's what we have seen so far. This is like the debug message for person.
I have a question. One of the things you said only works for traits that can be automatically implemented. What does automatically mean?
There.
Yeah. Also,
So what it means that it works only for traits which have already a procedural macro associated with them, like the debug, the PowerShell, and the one, yes, in the standard library, which provides a derived procedural macro for. So what I mean, and I will rephrase, it's if you create a trait, if you create your own trait, derive will not work with the trait you have implemented. Okay, you will have to create a procedural macro so that you can do this, implement the traits you have defined. So that's what it means. This works only because the standard library provides a procedural macro to derive the debug trait.
okay.
And this might be confusing because this is both a trait name and a procedural macro name. Look, if I click on it, actually it tells me macro debug. It's not like a trait. Derive macro generating an imp for the trait debug. Okay? But this is also a name of a trait.
So the easy confusion we can get because derive is not deriving a trait, it's deriving a macro.
No, it derive a trait, okay?
Okay.
But the macro, you have to name it the same way as your trait. So this is actually a macro, and this is not a trait. I don't know if that is clear. I understand it can bring confusion. Yes.
Yeah, I mean.
So you actually say you derive a trait, but yeah, this is like should be a procedural macro and not a trait, but it has the same name as the trait, so it kind of makes you abstraction. You say, because look, it's like derived trait name, but the trait name here should have like a derived macro associated with it.
Okay.
If there is none, it's not going to work. We can try if we define our trait greet there. We take that, copy. I've been too far. If we do greet, cannot find derived macro greet in this scope. So this is not because the trait exists that you can derive it, okay? Actually, this is normal because how the compiler would know how to implement greet for person? there is no way you can guess how you want grid to be implemented, right? So if you want to provide an implementation of grid for any structure or enum or whatever, you could do it by implementing a derived macro. Let's say, and this would typically be something you would do. You could get the structure name like that. You could say, I don't know, I provide a default implementation grid for every structure or enum, which is like I take the structure name and I say, I don't know, hello or whatever. And this is something you can easily do in a procedural macro because you have access to all that code and you will get access to the structure name, the fields, and so on. Is that clear?
I can see that also. I followed the debug and I saw that, yeah, there is the trait, and then right after you get the macros and the pub macro debug there, same name as you said.
Yeah.
And then there's a comment that compile a bit and so
Yeah.
it's not visible.
And something interesting is that if you are not happy with the way the trait is derived, you can always do it by hand. So you remove the derive directive, and you can there it's complaining, right? You see, because I don't implement debug. But now I can say I want to implement debug, but by hand. This is totally possible. No, I am name. Yes, of course, I have to use self. So if I'm not happy with the debug implementation of person, I can just implement it by myself by implementing the trait as it's expected. So this is like the way you implement FMT. So either for display or debug. This is like F is something you can write into. So you write this format string with these values inside F. This is like, yeah, something you have to remember and that you use everywhere when you want to implement display or debug. And pardon?
How do you get from the shorthand format when you call the double point question mark?
This?
No, you call double point question mark from debug to get the FMT function executed. But how can you define new shorthand formats like that?
A shorthand for?
Well, that one is basically going to call the FMT.
This is going to call that.
Exactly. But if I created my own trait and I wanted to create a simple notation like that to call a specific function.
In the format?
Yes.
No, you cannot do that.
No?
No.
Okay. So that's just hard coded for debug and
yeah.
Okay. So if I had my own trait, I would have to basically just call the function on P1. So P1.function name.
I don't get your question.
So if I implemented or if I created a new trait,
yes,
and implemented a function for it,
yes,
then I would specifically have to call that function on P1 to execute it. I wouldn't be, yes.
To print a custom version, for instance?
Well, or do something else, whatever I put in my trait as a function.
Yeah.
Okay. So I cannot create shorthand.
No, you cannot.
That's it.
No, this is not possible. Because again, this is like resolved at compile time. So this is something you will maybe realized one day is that you cannot provide to println like dynamic strings.
But this would also be the equivalent. I could also call the same result if I wrote p1.fmt, right?
Good question. No, I don't think so because it needs a formatter. You see,
Okay.
you can do maybe some custom around it, but just not. You cannot just call .fmt. So if I do that,
But if
I see,
that's the
hello, I'm
formatter.
Bob and I'm 42 years old.
But if I passed std fmt formatter also in the
There?
parameter, if I did p1.fmt below there and
Yeah, but I don't know what expects here as a parameter.
right, so I would have to see the implementation of
Yeah.
debug trait.
And you don't want to do that because it's complicated.
Yeah.
But yes, this is how you can, if you're not happy with the derive implementation, derive or just assumes that you want something pretty generic and implements it for you. But if you want something very custom, you would have to implement traits by hand.
I don't know if it helps or if it confuses more, but if you click on debug and press F12,
You can jump over the
but
You mean doing that?
no, on debug, yes, on F12. Right. Yeah.
Yeah, this is
And
the
then you
doc.
have the macro there. This visual. This is a great idea you have the macros.
Yeah, maybe something I can mention while we are in documentation like that. In Rust, what is nice is every example in the doc is run when you compile your tests. So when you write like your documentations like that, it's running every time you are testing your code. And so that in your documentation, you always have working examples, unless you publish code which doesn't pass the tests. Which should not be like the case for a lot of people, but okay. Finally, from and into traits, that's something we have touched a bit. So these are two traits that are used for type conversion. So to convert one type into another. And that you have it implemented for several types in the standard library, for instance, from strings to vec, or in case you need to do some wrapper as well when we saw that previously. So from is to convert from one type into your own type, and into is like to convert, no, it's backward. It's to convert from another type into yourself. And the into trait is to convert yourself into another type. And as I said earlier, these two are combined traits. So when you implement from, into gets directly generated for you. So you don't need to implement both of them. Thing you have to remember, never implement into, just implement from.
Why?
It's like that.
Okay.
Don't implement into, implement from. I think even like the compiler will tell you not to implement into. There is a reason, I don't remember what is the reason. So key relationship from and into are dual and of each other. That's what I said. Implementing from automatically gives you into. Into is more commonly used in generic bounds in case you want, for instance, to be able to convert one thing into another. Important notes from is preferred when implementing conversion and into when accepting parameters. Many standard library types implement these traits. That's something we have seen as well in the first chapters and a bit after as well, is that these conversions are taking ownership of the data. So after we call from or into, the data cannot be used in their originate types. And this also allows to be very efficient in terms of memory, because the compiler just, change the types and the data doesn't get deallocated and reallocated. So it's just like basically changing what is around the data, but not the data itself. Okay, it's very ergonomic. Yes, this is also important to understand, because for errors, for instance, you need to implement, if you are creating error wrapper types, you need to implement the from and into for every error you wrap. Otherwise, you might not be able to use the question mark operator. This is something, I don't know, maybe we are going to see that in the last example, because when we will do the project. So allow flexible function parameters, okay. Yeah, this is what I said, always implement from and use into if you want to put trait bounds in parameters. An interesting thing is that the conversion should infallible, so it should never fail. If we have the eventuality of failing, this is another trait we need to implement. This is an example of two structures, my U8 and my U64, one taking U8 and one taking U64. And we implement the conversion from one into the other, which takes one my U8 and which actually create my U64 from a my U8. So the method we need to implement is this one. Again, if I don't have this code block, if I just type fn, the Rust analyzer will create me the skeleton. So that's very convenient. Here is how to use it. My U8 42, and we create a my U8 from a my U8 64. And now you might understand what is the strange notation we see from the beginning with the string. So it means that string implements a method which takes a string slice. It has the implementation imp from string slice for string. And this is what we have been using since the beginning when we do string from and we put a string slice into it. This is actually leveraging the from implementation of the string type. So, okay. And the exercise is so why can we use my U8? Yes, because it's consuming, because from implementation, as we see, takes ownership over the value we pass as parameter. So here we take ownership over my U8. So the data from U8 is moved into the new type. Here. So there is no way we can change that.
Not clone to my U8 and my U6 clone.
Yes, yes, you can do that, but you kind of lose the benefit of having this mechanism if you clone every time something you do from. What is very interesting with that is that you keep the data and you just change the type around, but there is no memory overhead of doing such conversion. So just let's try to create a my U8 from a U8. So implement from U8 for my U8. And yes, something that you might see too is that when you get the from and into implementation, you could do, oh yeah, this is not a good example. Let's say this relates to type inference that we have seen since the beginning. If we know MU8 is a MyU8, I'm forcing the type here because by the usage we cannot the compiler cannot infer it because println is not expecting a strong type. This is a macro, and I'm forcing. We can do things like that when we have from and into. This is U8, and we can call dot into. Okay. Oh, sorry. This is something you will see a lot as well in Rust. And why? Because it knows you have a U8, you are expecting a my U32. The compiler knows there is a way to convert a my U8 into a U8 into a my U8. So you can call the into method and it will directly fetch the proper method, and it's exactly equivalent to this. But there you don't need the type, right? Because it's already implicit because of this. What's your question, Andras? This?
Yeah.
This is just a way to define the U8.
It's like 832.
Okay.
Yeah, this is you can add like the type at the end of the integer to force being a U8. So this works. So you will see a lot like into. We could have used like the string into works as well if let s equal, but we need to force the type as well here. We do test dot into. This works. Yeah, I put equal. this works because it knows its strings. We expect a strings. It has a method to map a static string slice into a strings, so it applies it. I tend to like a bit less this syntax because at the end you don't really know what it's mapping to, especially if the type of S is inferred by a further method call or something like this. So you might actually lose a bit what the data is when you do into. So I tend to prefer to use this notation, like the type namespace from and the value from. This is just a matter of preference, but I know I'm using into at some places, but yeah, I don't have like clear guidelines for this usage or not. So what was the question? So implement the from and into. So my U8, we can do 42 U8 dot, no. Okay. Yeah, it's complaining. Why? Okay. Okay. It works. And we could even imagine like to convert it back to U8. This is totally useless, huh? Right? But it's just to show that is not satisfied. Why? You have my U8 and U8. Okay. It doesn't implement the into for U8 then. The from. Okay. It implements the into but not the from. Okay. So it doesn't work like this. We could do this then if we want it.
Implement
This
from my U64 for my
yeah,
U8.
yeah, we could do that. This would work then. No?
No, because you don't implement any way of this conversion.
Of the reverse conversion. Yeah, yeah,
I think.
that's right. I would have to do that. Yeah, my U8 or U8. Okay. This works now. And yeah, as you saw here, so we implement a trait for a type which is in the standard library. So this is okay because we have like this, which is defined in our create. We cannot like override from or into also for external structures. Otherwise, it could create like a huge mess in the packages and libraries. Okay, this would work too now. This is totally useless, but it works. you switch one to the other and switch back. So yes, that's it about trades from and into, which is something very powerful. We would have to see with errors because errors. Maybe this is something we can talk during the last session. There are very convenient methods, and I mean not methods, but ways to deal with errors in Rust, and just by using a crate developed by David Tolnay. And this facilitates a lot, like the mapping between error types, so that you don't have to implement all these from and into errors by yourself, which might be painful for error handling. So that's about it for the traits. If you have questions or whatever, this is the moment. And if not, let's see in 45 minutes so that we can keep our 45-minute breaks and we can finish with the small projects, which should make use of most of the thing we have used and seen so far. Are you good, the remote guys?
Yep, all good.
Okay, great. I will stop the recording and see you in 45 minutes then.
Yep. See you in 45 minutes.
Bye.